Good morning, students. Today we will discuss about properties of pure substance. In this, the behavior of pure substance, phase transformation from the solid to the superheated steam, and the properties. What is the quality of steam? How we can calculate the properties? Internal energy, enthalpy, entropy, how much heat is transferred by using the steam tables and Mollier diagram. Next, identification of and simple problems on quality and dryness fraction and throttling also. We are calculating throttling also. Coming to the pure substance. What is pure substance? Once we know the pure substance definition, then we can identify the what is the example of the substance, the medium. The chemical composition with respect to phase, it is not changing. The chemical composition with respect to phase is not changing, then it is called pure substance. In the universe, God gifted pure substance are one is only one, that is water. In solid form, ice; in liquid form, water; in vapor form, steam. In three phases, the chemical composition is same H2. But because while we are running the power plant, different components have dealing different phases, and two-phase system also, single component is dealing two-phase systems like turbine. We are expanding steam, but last stages of blade exposed to the wet steam, water droplets will start. So their water droplets is there, and so steam also is there. If chemical composition is changing with respect to phase, means the life of the plant will reduce drastically. That is one drawback. That's why while we are taking a working fluid, especially in power generation, pure substance we are selecting. The God gifted pure substance in the universe is water. That's why more than 3 lakh megawatt thermal power plants are available in India, especially in India itself, not entire world. All are based on the steam power plant. The source, thermal source is different. It may be nuclear, it may be coal, it may be gas, but cycle and working fluid is same. So in this unit we are thoroughly studying the only water, only related to steam or water. So what is the phase transformation? Solid minus 20 degrees ice to the phase transformation of the pure substance water, minus 20 degrees to more than 100 superheated steam. Solid ice to superheated steam. So how many phase transformations are there? Stages. So minus 20 degrees ice to 0 degrees ice. First it is moving. Minus 20 to 0 degrees ice. Next 0 degrees ice to 0 degrees water. Here phase transformation is coming. 335 kilojoules per kg of the energy. If I am giving this ice, will 0 degrees ice will convert as a 0 degrees water at 1 atmosphere pressure, not again on pressures. Next 0 degrees water we will convert as a 100 degrees water. It's the sensible heat, MCP delta T. Water specificity is 4.2. Next 100 degrees water to 100 degrees steam. Here 2250 kilojoules per kg of heat we are supplying, then only the water at 100 degrees will convert as a steam at 100 degrees. Now here also one condition is there, 1 atmospheric pressure. Then after 100 degrees steam to the next further superheated range. This entire phase transformation I shown at 1 atmospheric pressure. But in total phase transformation, especially for power generation, This solid to superheated steam is not required for study. How much is required? We will concentrate our boundaries only. This is the TS diagram, temperature and entropy. This curve is called saturation curve of the water, pure substance. Saturation curve, this side is liquid. Upon the saturation curve, this is called saturation liquid. And upon this side, upon the saturation curve is saturated vapor. This side is superheated vapor. So this side is liquid, this side is vapor. Inside the saturation curve, the phase transformation will occur from liquid to the solid. Okay. So here we required this stage is called subcooled. This is the saturation liquid. This is the saturation vapor. These 2 points we can extract directly from the steam table, from table number 1 or table number 2. Table number 1 temperature based, table number 2 pressure based. Generally we are calculating pressure based. So from the table number 2 you can extract the properties directly, saturation liquid and saturation vapor. Less than saturation liquid, whatever is there, subcooled liquid. This stage is called subcooled liquid. From the saturation liquid to saturation vapor we are converting. This stage is called wet region. If saturation liquid to saturation vapor, while we are supplying heat, the phase transformation will occur. So how much wetness is there, how much dryness is there, how we are calculating means based on the dryness fraction. X, we are represented by X, mass of vapor by mass of vapor plus mass of vapor. While we are supplying heat, mass of vapor is increasing. It's a common criteria. We are supplying heat, mass of vapor continuously increasing. So at particular point it will reach 100% vapor. Then dryness fraction is 1. If dryness fraction is 1, it is a saturated vapor. If dryness fraction is 0, it is a saturation. In between the wet region, wet region is continuing. But you see, saturation liquid, saturation vapor and wet region, the temperature is constant. There is no change in temperature. Phase transformation is there. At saturation liquid to saturation vapor, the phase transformation of wet region, these three regions, temperature is constant. Next, superheated region. Saturated vapor plus remaining is sensible. Here saturation liquid minus remaining is sensible. So this phase transformation is sufficient for calculating the performance of the power plants, not subcooled solid to superheated vapor. Here only subcooled liquid to superheated vapor. Only this phase transformation is important for us for calculating the problems. So here you can see, so subcooled liquid stage is required, saturation liquid, saturation vapor and wet region and superheated. Saturation liquid, saturation vapor we can extract from table number 2 of steam tables. This superheated also majoritarily we can extract from the superheated tables. We don't want to calculate table number 3 to 5. Superheated table for specific volume, superheated table for specific enthalpy, superheated table for specific entropy. If it is out of the box, then only we are calculating. So I think this phase transformation is more than sufficient for our calculations. These are the stages. I already mentioned this. Now how we are extracting the properties. At wet region, if you know the dryness fraction, HF, I already mentioned, enthalpy at liquid stage plus X into Hg minus HF, enthalpy at saturated vapor minus enthalpy of liquid. But we want to know the dryness fraction. At wet region, we want to calculate the properties like entropy, SF plus X into Sg minus SF, and internal energy also EF, but internal energy we are not extracting from the steam tables. How we are calculating? We are calculating enthalpy. Enthalpy equal to internal energy plus flow work. So internal energy equal to enthalpy minus flow work. Flow work equal to pressure into volume. That's all. Like that we are calculating the internal energy. Next specific volume also same. Vx equal to Vf plus x into Vg minus Vf at wet region. Coming to superheated region, up to Hg saturated vapor we are extracting from the steam tables plus sensible heat, this one specific heat into T superheat minus T saturation. If specific heat of steam is provided in the problem, then you can calculate T superheat minus T saturation, or S superheat also, like SG entropy of vapor, saturated vapor, plus the remaining is sensible entropy Cp into Ln T superheat by T saturation. Coming to the volumes, in vapor means it is a gas, we can assume as a gas. We can apply gas laws, Charles law. Volume to temperature ratio is a constant. So, volume of specific volume of superheated steam by temperature of superheated steam equal to specific volume of saturated vapor by temperature of saturated vapor. Here, volume of saturated vapor, specific volume of saturated vapor we can extract from the steam tables. Temperature of the saturation table, temperature also we can extract steam tables. T superheat it will give in problem. Then we can calculate the specific volume at superheated conditions. Like subcooled also say HF, it is less than the saturated liquid enthalpy. HF minus Cp into T saturated minus T subcooled. These are also like that only. S subcooled also SF minus Cp into Ln T saturated. But volume point of view, in liquids, a saturated liquid or subcooled liquid, the change in specific volume is negligible. Why? Because in liquid specific volume is 0.001 meter cube per kg. Further reduction of temperature also, the negligible amount of change in specific volume. That's why specific volume at subcooled and saturation liquid is same. These are the properties we are extracting. Next, Mollier diagram. Actually, Mollier is recognized in flow process the importance of relation between enthalpy and entropy. Because for determination of the availability, you want to know total energy, you want to know unavailable energy. Then only you can calculate the exergy or capability to do work or availability or available energy, whatever. That is very important. So, in y-axis he took enthalpy and x-axis is entropy. The major curve is, this is the saturation curve in Mollier diagram. You can see dryness fraction is 1, x value is 1. This is the saturation curve. Dryness fraction is 1. Next, downward, the dryness fraction is further reduced to similar saturation curves are continuing. 0.95 dryness fraction, 0.9, 0.85, 0.8, 0.75, 0.7. So, dryness fraction, different dryness fraction lines. Next, these are the pressure lines. You can see inside the saturation curve, the pressure lines and temperature lines are both are same. But after crossing the saturation curve, the pressure lines are same angle of deviation is there, but temperature lines are deviating. You can see 50 degrees, 100 degrees, 200 degrees. These are the temperature lines. Horizontally it is deviating. So this is the representation. This is the superheated region. This is the wet region. Subcooled region they are not represented in Mollier diagram. So by using Mollier diagram, you can calculate wet region and superheated region properties directly. You can extract. Now we will solve some problems, then you will get the clear idea about Mollier diagram. Next. one more process, that is next. Coming to the throttling, we already discussed in refrigeration and air conditioning. Throttling main purpose, reduce the pressure. Well, what is the main condition? Which purpose we are reducing in refrigeration and air conditioning? For achievement of desired temperatures. What is the condition means? Without changing the heat value, enthalpy, we are reducing the pressure to achieve the desired temperatures. The one application in refrigeration and air conditioning. But in general application, throttling, to increase the dryness fraction of the steam. Suppose at so at 1 bar pressure, 1.01 bar pressure, saturated steam temperature is 100 degrees. Suppose my steam temperature is 90 degrees. Then it is a wet steam only, not a dry steam, liquid condition. Now I want to increase the dryness fraction. What I am doing? I am reducing the pressure without changing the heat value. Instead of 1 bar, I am meeting zero point 0.5 bar. The saturation temperature is 89. My temperature is 90 or 95. I will get superheated steam. So increase the dryness fraction. Actually, in all thermal industries, throttling is the common process. Major thermal power plants, thermal utilization, paper and pulp industry. After in turbine, after expansion, we are getting the wet steam. So we want to move to the superheated range. We are reducing the pressure. So what are the conditions for reduction of pressure? Enthalpy is constant, that is the first condition. Second one, pressure is dropping, increasing in volume, increasing in entropy. So in the TS, in HS diagram, in enthalpy and entropy diagram, Mollier chart you can represent. This is the saturation curve. Initially it is having the some wet region, then some 0.95 or zero point 0.9. Isoenthalpy is trying we are moving to next pressure, expanding into next pressure from 1 bar to zero point 0.5 bar something. Then we are reaching superheated range or some dryness fraction is increasing. Okay, so entropy is increasing. Enthalpy is constant. Enthalpy is constant, but entropy increasing by throttling process. And if we are assuming it is a adiabatic one, then the heat transfer is zero. Throttling, we are not producing any work. These are the conditions of the throttling process. How we are determining the final condition of the steam? One best process. Open the Mollier diagram. Mark the initial condition, whatever the dryness fraction. Move isoenthalpy to next expansion. To next expansion pressure, whatever pressure they give. What is the condition? If it is moved to the superheated range, then write the equation. Initial condition is wet region, no doubt. So H1 plus X into X1 into HFG at P1 pressure, HF plus X into HFG at P1 pressure equal to, because enthalpy is constant. Next one, it is superheated condition, then Hg into Cp into T superheat minus T saturation. Determine the T superheated condition. Our next condition, by representation of Mollier diagram itself, we came to know next condition also wet condition. Write down the same equation at P2 pressure and determine the dryness fraction. So simplest simple method. Throttling easily we can calculate by using the Mollier diagram. I will use some examples, then you will get the clear idea about throttling. So one problem you can see. A 1 kg of steam at 14 bar pressure and dryness fraction of 0.9 throttled to 1.4 bar pressure. So simple problem. Initial mass is they given 1 kg. So specific enthalpy we can consider. Next, 14 bar pressure and dryness fraction is 0.9. So initial pressure is 14 bar and dryness fraction is 0.9. It is not a saturated steam. It's a wet region. Now we are throttling. For which purpose? To enhance the dryness fraction. Okay, 0.9 to how much is enhanced? Up to reaching 1.4 bar. Determine the final condition of the steam by using steam table and boiler diagram. I already mentioned, better you can consider the Mollier diagram. It is easy for us. See, mark initial condition 14 bar pressure. This is a 20 bar pressure, less than 20 bar. So for somewhere 15, 14 bar pressure and zero point 0.9 dryness fraction. This is the dryness fraction. It's a zero point 0.9 dryness fraction. What is the condition? Throttling means isoenthalpy. This is the vertical line, y-axis is the enthalpy line. So horizontally I am moving. So I am not changing enthalpy. Horizontally I am moving up to what pressure? 1.4 bar pressure. You see, this is the 1 bar pressure line. So this is the 1 bar pressure line, more than 1 bar, up to 1.4 bar pressure we are. So it is not reached to superheated range. It is wet region only, but the dryness fraction is increasing 0.9 to somewhere 0.95, above 0.95. So now we can write the equation. Enthalpy is constant, so H14 yeah, the wet steam enthalpy at 14 bar HF plus X into HFG we can calculate. Next, Hx value at 1.4 bar. Already from the steam table, from the Mollier diagram, it is a wet region only. A same wet region equation at 1.4 bar, Hf plus x1 into Hfg. This dryness fraction now we can calculate how much we are getting. This is the dryness fraction x value. X value you can get. This is around x value is 0.956. So simple method. So throttling, it is easy to calculate by using the Mollier diagram compared to general calculation. One more problem. In a throttling calorimeter, the pressure of the steam measured before and after throttling are 16 bar and 1 bar represented. Earlier 14 bar and 1.4 bar. Now 16 bar and 1 bar pressure. Find the dryness fraction of steam before passing through the calorimeter if the temperature of after throttling is 150. So now starting of the throttling, what is the dryness fraction? Here you don't want required any Mollier diagram also, because end condition they given, that is superheated. So end condition H2, H1 equal to H2, H2 equal to Hg plus C, specific heat to T superheat minus T saturation. You can calculate the H2 value, because specific heat also given in the problem 2.1 kilojoules per kg Kelvin. H1 it is a wet region, Hf plus X into Hfg. You don't know the X value only. You substitute equal isoenthalpy process H1 equal to H2. This H1 at 16 bar pressure, determine the X value. X value initial condition, it is coming 0.9945 dryness fraction. Means almost to saturated steam we are converted as a superheated steam. Same one you can calculate by using the Mollier diagrams. Now you first mark the final condition. At 1 bar pressure, you see 150 degree centigrade. At 1 bar pressure, 150 degree centigrade. See, yes, this is the 1 bar pressure and it is a 150 degree centigrade. Initially you mark the final condition. Isoenthalpy we are moving to 16 bar. 16 bar to 1 bar we moved, but we know the final condition, we don't know the initial condition. So first I marked the final condition 1 bar and 150 degree centigrade. You see it is reaching almost upon the saturation curve. That is only x value 0.99. So in both way you can calculate initial and final conditions throttling process. Mollier chart is easy compared to general calculation. And next one, by the phase transformation of the pure substance, what is the heat interactions? That questions you can expect in competition exams or end exams from this unit. You see, 680 kgs of fish at 5 degrees are to be frozen and stored at minus 12 degrees centigrade. At present 5 degrees centigrade fish is available. It is frozen to minus 12 degrees centigrade. The specific heat of the fish above the freezing point is 3.182. Water we consider 4.2. But fish is 3.182. And below the freezing point is 1.717 kilojoules per kg. The freezing point is minus 2 degrees. Generally, water at atmosphere pressure, we are considering freezing point is 0. But here is minus 2 degrees. That is only difference. The latent heat of fusion, general water we consider 335 kilojoules per kg. But here 234.5. How much of heat is removed? And second one, what is the percentage of latent heat? Okay. First, how much of heat is removed means 12 degrees to minus 2 degrees. One is sensible, 680 into specific heat. Next, latent heat minus 2 degrees to minus 2 degrees freezing. So, same. Latent heat they given 234.5 into what is the mass? 680 plus further reduction minus next, sorry, reverse we. First 5 degrees to minus 2 degrees, 5 degrees to minus 2 degrees, minus 2 degrees to freezing to minus 2 degrees freezing. Next to minus 2 degrees to minus 12 degrees further freezing is taking place. This is the sensible heat. Sensible heat, the sensible heat specific heat is already given 1.717. Finally, we are getting some megajoules, 186.284 megajoules. Our latent heat ratio, this is the latent heat. Major ratio is latent heat only. So, majorly we want to extract latent heat compared to sensible heat to freeze the fish from 5 degrees to minus 12 degrees. Same method. Calculate the amount of heat required to convert 100 kgs of ice to ice at minus 10 degrees to 100 degrees of at normal pressure, steam. So minus degrees ice, 10 degrees ice to steam. Here latent heat of the ice is, the specific heat of the ice is 2.1 kilojoules per kg Kelvin. Instead of that they given 2100 joules per kg Kelvin. Latent heat of fusion of ice is 3.36 into 10 power 5 joules per kg. Instead of that 336 kilojoules per kg. Next, specific heat of water we know 4.2 kilojoules per kg Kelvin. Here given 4200.5. And latent heat of vaporization of water. This is also 2250 kilojoules per kg. Here they given 2.25 into 10 power 6 joules per kg. Just first you convert the units. First minus 10 degrees to 0 degrees ice, 0 degrees ice to 0 degrees water. This is the latent heat 3336. Next 0 degrees water to 100 degrees water. Here mass into 100 into specific heat is 4.2 and temperature difference is 100. This is the sensible heat. Then after 100 degrees water to 100 degrees steam, what is the latent heat is required? This latent heat is around 2250 into 100 kgs. Total heat removal is 3.3 into 10 power 6 joules or 3000 kilojoules of heat required. This is a simple calculation. Whatever the values may be, you can cross verify later. This is the methodology. Some more problems commonly on properties of steam we can solve. The remaining you can practice yourself. Find the specific volume, enthalpy, and internal energy of wet steam at 20 bar pressure with the dryness fraction is 0.8. So wet region we want to calculate. Specific volume, enthalpy, internal energy. I already mentioned internal energy not directly we are calculating from the steam tables. First we will calculate the enthalpy. Then after enthalpy minus flow work, pressure into volume, you will get the internal energy. So if wet region already we discussed it. At wet region enthalpy we want to determine is enthalpy at saturated liquid plus x into enthalpy at saturated vapor minus saturated liquid, like specific volume also. So extract the properties at 20 bar pressure, enthalpy at saturated liquid, enthalpy at saturated vapor, specific volume at saturated liquid, specific volume at saturated vapor, and calculate the Hx and Vx value. Then after Ux equal to Hx minus Pv. Here pressure in bars, but here we want to substitute pressure in kilonewton per meter square. Kilonewton per meter square means 1 bar equal to 100 kilonewton per meter square. That's why minus 20 into 100. We are not placed this 100 means this value will change. This is one concentration on units and dimensions. Second problem, see, simple problems. If we are capable to extract the properties from the steam tables, it is not a big task. Next one, in a steam generator, compressed liquid water at 10 megapascal, 30 degrees centigrade, a 30 mm diameter tube at the rate of 3 liters per second. Steam at 9 megapascals, 400 degrees centigrade, exit the tube. Find the rate of heat transfer to the water. Indirectly, shell and tube boiler indirectly. In shell, flame, and tube water. Finally, inlet water is 10 megapascal. Outlet water is 9 megapascal. Means some pressure drop is there, no doubt at all. And inlet condition they given 10 megapascal 30 degrees centigrade. Here megapascal they given in steam tables pressure in bars. So for extracting of properties, first this megapascal you convert into bar. 10 megapascal means 1000 kilopascals. 100 kilopascal equal to 1 bar. So 1000 kilopascal means 10 bar. 1 megapascal equal to 10 bar. 10 megapascal means 100 bar. This unit conversion is required. So at 100 bar pressure, 30 degrees centigrade. You see 100 bar pressure, the saturation temperature is 300 level. Means it is a subcooled region. Subcooled region, how we are calculating? Saturated liquid minus specific heat of the water into T saturated minus T subcooled. Calculate the enthalpy at 100 bar pressure. Next condition, the exit condition of the boiler, it is the steam, superheated condition steam at 9 megapascal, means 90 bar pressure. 90 bar pressure, 400 degrees centigrade from the table number 4, I think. From table number 4 directly you can extract. Otherwise, you can calculate Hg plus Cp into T superheat minus T saturation. You will get the value. Rate of heat transfer means mass flow rate the already given 3 liter per second, 3 into steam enthalpy at exit minus water enthalpy at inlet. The difference only the rate of heat transfer. Simple problems. Next one. Calculate the enthalpy and entropy of steam at 10 bar when it is saturated, 0.95 dryness fraction, and superheated to 360. Simple. Saturated means 10 bar pressure, HF value, SF value, HG value, SG value extract. The first question is completed. 0.95 dryness fraction. Determine the enthalpy at 0.9 dryness fraction and entropy also. In superheated condition, H superheat equal to Hg plus Cp into T superheat minus T saturation. S superheat equal to Sg plus Cp into ln of T superheat by T saturation. Why? Because why we are calculating here they given specific heat and also they given 260 degrees centigrade. In steam tables, superheated tables, 250, 300, 350 like that is available. Not 260, 270. So in this condition you have to calculate yourself. Next one, determine the entropy per kg of steam at 2 megapascal if the condition is dry saturated, 15% wet, and third one is superheated to 300 degrees centigrade. So in this condition you first is dry saturated 2 megapascal. I already mentioned 1 megapascal equal to 10 bar, 2 megapascal means 20 bar. So at 20 bar pressure, dry saturated means, so saturated vapor property entropy you can extract. Only they asked entropy only. Next one, 15% wet. Wet they given, not dry. So 15% wet means 85% is dry. Means the dryness fraction is 85%. Wetness is 50% means the dryness fraction is 85. This is only the one point we want to consider. If we know the dryness fraction 85, then we calculate the SF plus X into Sg minus SF and T superheat. Instead of calculating 300 degrees from table number 5, I think you can extract directly, you will get the same value. So simple problem. Here one main observation. First, megapascal convert to bar. Second one, here they given wetness condition, not dryness factor. This question generally repeatedly asking. A simple problem but repeatedly asking. A spherical shell of diameter is 50 centimeters contains steam at a pressure of 40 bar and 0.85 dryness fraction. Calculate the mass of water and mass of steam. First we can calculate 40 bar pressure, in bar only they given, dryness fraction 0.85. Extract the specific volume of saturated liquid and saturated vapor. Determine the specific volume at that dryness fraction 0.85. Vapor you will get some value, and determine the volume of the vessel, actual volume of the vessel. Vapor volume at that 0.85 dryness fraction, vapor specific volume we determined some 0.04247445 meter cube per kg. Actual volume of the shell, how we are determining? Diameter they given 4 by 3 pi r cube. Convert into meters, it is a 0.5 meter. Diameter we want a radius 0.5 by 2, 0.25. So total volume you know, divided by specific volume of vapor, you will get the mass of vapor. The mass of vapor is 1.548. Dryness fraction already given 0.85. Dryness fraction, what is the equation? Mass of vapor by mass of vapor plus mass of liquid, mass of water. So mass of water, automatically substitute mass of vapor, you will get the mass of water is 0.2731. Simple problem. Repeatedly this question is asking in competition exams. This question also continuously asking. It's also simple problem. A vessel of 0.4 meter cube capacity contains 2 kg of mixture of water and steam in equilibrium at a pressure of 6 bar. The given pressure 6 bar. Calculate volume and mass of liquid and volume and mass of vapor. You see, vessel specific volume, it is the vessel, the volume divided by mass, you will get the specific volume. Total volume is 0.4 divided by mass is 2 kgs. 0.4 divided by 2, 0.2 meter cube per kg. This is the specific volume of the wet steam. This is the specific volume of the wet steam. Then determine the X value, dryness fraction. We know the specific volume of the wet steam is a 0.2 meter cube per kg equal to Vf plus X into Vg minus Vf. Extract the properties at 6 bar pressure and calculate the X value. X dryness fraction is 0.6322. Mass of vapor, total mass is 2 kgs and dryness fraction we multiply, you will get the mass of vapor. and mass of liquid. Once we know the mass of vapor, total mass we know 2 kgs. So 2 into 1 minus 0.6 or 2 minus 1.264, you will get a 0.736. Next, volume occupied by the vapor. This is the mass of vapor and specific volume of the vapor Vg. You multiply with the Vg, you will get the volume occupied by the vapor. Next, volume occupied by liquid. This is the mass of liquid and so volume occupied by the liquid is mass of the liquid into specific volume of the liquid Vf value. You will get the volume. Simple problems. Next one. Here the specific volume of the steam at 10 bar pressure is recorded. Find the quality of steam, enthalpy and internals. Quality. Vx value already given. 10 bar pressure, you extract the Vg and Vf value, determine the X value. That is only the quality of steam. Once you know the X value, determine the enthalpy at that dryness fraction. Enthalpy and internal energy, I already mentioned. Internal energy equal to enthalpy minus flow work. You will get the final value. So these are the simple problems upon the properties of steam. Actually, in this unit, just we introduced how to extract the property, how to calculate. In next applied thermodynamics, we will solve the problems. How the performance of the power plant we can enhance, and what are the heat losses are going, what is the isoentropic efficiency, everything we will solve. So in this unit, just we are extracting the properties. Next, we are utilizing that properties for the performance analysis of the power plants. Thank you very much.